Hello everyone, my name is Roy Jafari and I would like to welcome you to another video of data mining series. In this video we're going to continue talking about dimension reduction. In the previous video we did talk about supervised dimension reduction, and we learned about two methods we could be using for supervised dimension reduction. In this video we're going to learn two new methods and see how they are different and learn about their advantages and disadvantages. So let's look at this slide. Alright, so in this video we're going to again learn the difference between supervised and unsupervised dimension reduction. It's something we already discussed in the previous video. Just a quick recap, and then we will pick up where we left off as when we were talking about the weaknesses and the strength of decision trees, and then we built on that to learn about two new methods, and we're going to learn how we would go about dimension reduction using random forest and brute force computational dimension reduction, which are both still supervised dimension reduction methods. Alright, so we did talk about, there are two types of dimension reductions: numerosity dimension reduction and dimensionality dimension reduction. Numerosity dimension reduction, we want to reduce the number of rows. Dimensionality dimension reduction, we want to, numerosity data reduction, we want to reduce the number of rows, and dimensionality data reduction, we want to reduce the number of dimensions or the attributes. We have two types of dimension reduction: supervised and unsupervised. Supervised, as we said, is basically the dimension reduction that we would do previous to classification or prediction task. Anytime we are connecting independent attributes to a dependent attribute, and us finding the best subset of the independent attributes for the success of this connection and the prediction task and classification task, it's called supervised dimension reduction. And of course there is unsupervised dimension reduction, which is not what we're going to discuss in this video. It's going to be basically us reducing the dimensions by the goal of reducing the size of the data as having less number of attributes, but keeping most important part of the information in the data set, which is something that we'll see in the future videos. So, when we were talking about decision tree, we discussed how decision tree is a great visual tool to give us dimensions that are important. But at the same time, if you pay attention here, it's very hard for us to really know which attribute is more important. I mean, is it the ones that are on top of the decision tree or closer to the root? Or is it the fact that if an attribute is happening or occurring in the decision tree more often? And that creates a challenge for us, and that's the disadvantage of the decision tree. But with random forest, that is going to be dealt with. So we're going to see a method that's not going to have this specific shortcoming. So random forest is basically an algorithm that uses more than one decision tree. I mean, it uses more than one shallow decision tree, right? If you compare this decision tree, this is has as much as needs be. It has roots and it has branches as much as the application needs it. But random forest instead uses only small decision trees, only like one sort of like a level, and these are called weak decision trees or weak classifiers. And it creates more than one of them. Like you can see here, for example, it has created so many decision trees, and these decision trees are created randomly, and there is a randomness nature inside them. And by doing all of these decision trees, then once this is done, it combines the opinions of all of these weaker classifiers to come to one decision or one prediction or one classification. prediction, one prediction or classification. So basically, it combines all the results of all those decision trees to come to a prediction or classification. So random forest is ensemble based algorithm. Every time you have more than one algorithm inside an algorithm and sort of like use them in a combined fashion to come to a final conclusion, that's called ensemble algorithm. And of course, it can both handle classification and prediction as we discussed. But what is interesting for us as far as random forest being able to do dimensionality reduction is its unique design of the algorithm. I mean, using so many different decision trees gives us the opportunity to sort of get an insight on, relative importance of each of these attributes, each of these independent attributes, just by, checking how often one independent attribute appeared in these decision trees. Then it gives us an insight on which one is perhaps more important. So that's all there is to it. Random forest basically, let's say, has 1,000, weaker decision trees, and then you say, okay, out of these 1,000 weaker decision trees, I don't know, this independent attribute appeared 700 times. So probably 70% you could say it's important, that attribute, for the task of predicting that prediction or classification task. So that's exactly that. For example, in the previous example, this is what we would get in decision tree, but random forest gives us basically a percentage-wise output. It says 20% of the time complaints appeared. Second of use appeared 15% of the time. Frequency of use appeared 12% of the time, and so on and so forth. And it gives us a ranked version of these attributes, so we do know which one is more important perhaps than the other ones. It doesn't have the weakness of the decision tree that it was really hard for us to decide which one the independent attribute was more important. So random forest doesn't have that issue. So this is the random forest. But random forest still has a big problem. We do see this, we say, okay, complaints is 20% important, second of use is 15% important. But how do we know what to keep or what to, discard? Do we say, okay, let me discard these? Or do we say, let's keep everything? Or do we say, let's just keep the first 3 and discard the rest? We just don't know. I mean, these are just percentages that it's giving us. I mean, it gives us a ranking, and in itself, it could be useful, for analytics, but it doesn't really give us a concrete and final answer as far as what it is that we want to use here. Right, so that's the weakness of random forest. We don't know how to decide. We don't know what subset we need to use. And the next method we are going to learn is going to take care of that. So the next method is brute force computational dimension reduction. Basically, it's experimenting with all the possible combinations of the independent attributes for an algorithm to see which one works best for that specific algorithm. And it's best, the second point here, you can see it is best to actually see this as a part of the tuning, right? For example, you have K and N, and you want to use brute force computational dimension reduction as well. I mean, whenever you are tuning for K, what is the best number of K, you would also tune what is the best subset of the independent attributes. So you can sort of see it as a tuning process when you are using this. So for example, here we are tackling the dimension reduction using k-means, using brute force dimension reduction, brute force computational dimension reduction, and we are mixing it with k-means. So you can see in the beginning we only are using the first, just only one attribute, right? So it's only one attribute, and then you move to 2 attributes, and so on and so forth. You start moving to 3 attributes, and by the time you come to yourself, you will have noticed that you have experimented so many different one of these, and every time you experiment with them, you find the best K, and then you will find what is the performance of this subset, and then by having reached there, then you come to this final result. You can sort everything, and you will come to see, for example, there are two subsets, which are these two, that if you use them, you get to around 99% accuracy, right? So you actually know what is the best subset, right? So you were able to find the best subset for this algorithm. These were two of the weaknesses of a random forest, right? The random forest was specific to random forest, but here brute force can be combined with any algorithm, right? You can do brute force with MLP, KNN, any algorithm you want. You can combine it with brute force, computational dimension reduction. And another thing was about random forest. It was hard for us to make a final decision, right? Do you remember? It was like, do we keep the first three? Do we, keep, the ones that are higher than 5%? It's very subjective. We don't have a final answer there. But here, it actually decides for us. It says this is the subset. You should use these three. And that's the advantage. These are the advantages of brute force computational dimension reduction. Of course, the other advantages is it being non-linear, and also it being calculating the interactions, or like considering the interaction between the independent attributes. All of those are here as well, but it has a very big weakness. It's computationally very expensive, as you would imagine, and that's in itself is enough for you, or most of the time, to maybe sometimes rule this out, because it's just computationally too expensive. So anyway, let's move to the next slide, which is a summary of this video. So in this video, we sort of had a recap about what is supervised dimension reduction, and then we learned about two new methods, random forest and computational dimension reduction, and we did see the weaknesses and the strength of them, and how these could be selected as one of your dimension reduction methods. Until the next video.